Welcome to FGC HRI IPM Joint Number Theory Seminar Series. Today our speaker is Emre Sertöz from Leiden University, and he will going to talk on his recent research computing linear relations between univariate integrals, a very ambitious project apparently, and we are very happy to have him in our seminar series. So please, Emre.
Thank you very much for the introduction and the invitation to speak here. It's my pleasure to be here. And if you cannot hear me, so if my voice goes down as I move in that direction, please let me know. I have another trick up my sleeve, and we'll fix this as we go. All right, so the talk is about computing linear relations, and this is joint work with two collaborators, Joel Lockman. He's from the Max Planck Institute for Software Systems, and also James Ben Worrell from Oxford. He's from computer science department in Oxford, and this is half the fun. So we actually started this project with kind of applications in mind to discrete dynamical systems. This is actually what they study. Although they're computer scientists, they translate these computers into discrete dynamical systems. And well, the project turned out to be very ambitious indeed. And so now this is the heart of it, is the main project, which is to find the linear relations between certain kinds of integrals. And I'll start with a sort of a general kind of historical introduction. So the whole thing, although I'm interested in computing linear relations, a special case of this is much more famous, let's say. So we've all heard of this. And this is deciding if a number is transcendental or not. And I'll come back to this. One is going to be among the integrals that I'm allowed to use. So Q-bar linear relations will allow me to check for transcendence. And so let's do this. Then let's talk about transcendence just a little bit. And historically, although there was an idea of transcendence for other kinds of objects, it was not applied to numbers. I think they were just looking at numbers in a way that was, first of all, it would have been a difficult question, and also the numbers just kind of popped out of functions. So they considered transcendence of functions, but not numbers, until Euler seems to have coined the term. And this is 1755. He coins the term for a transcendental number. Meaning a number that does not satisfy a polynomial relation with integer coefficients. And he already at that time suspects that pi is not algebraic, so suspects pi is transcendental. But at that time, no one knows if even there are transcendental numbers. So that I suspect that they had the same intuition as Euler, that probably there were transcendental numbers. But the problem is proving these things. And it took almost 100 years before the first development. And this is Liouville. This is 1844, I think. First and foremost, he says there are transcendental numbers. And in particular, he gives one example, which would be the sum of 10 to the minus n factorial. So his trick was, well, he had realized that if you have an algebraic number, you cannot approximate those algebraic numbers very efficiently. So that kind of repels every rational approximation. Whereas this one, already the partial sums gives you an insanely fast converging rational approximation. And therefore, within his theory, that he could show that this number cannot be an algebraic number, hence it's transcendental. And it's the first result that this shows that there are transcendental numbers. And now I'll quickly go over the next century, basically. So let me get these dates right. Hermite in 1873. So he's the first one to show that there are, well, to show the transcendence of a number of interests. And so a naturally occurring homegrown number, one could say is E. E is transcendental. So whereas Liouville engineered the number to fit his theory, they had to engineer their techniques to fit a naturally occurring number. And we'll kind of go in that direction as well. And of course, Lindemann at least completes the proof that pi is transcendental. I mean, it's more than 100 years after Euler suspects this, and it shows you that it's very hard to show that a number is transcendental. And still, actually, the kind of their proofs have been refined over a century, 150 years even, and still it's kind of tricky. So we didn't have a good theory until very recently to handle these kind of numbers. E doesn't really fit into our theories, but we can handle pi, for example, now efficiently. And the state of the subject was mostly that you'd have to deal with every number using new tricks specific to that number. So the field is maturing, perhaps from the late 1980s onwards, especially recently, so that we can talk about systematically dealing with many numbers at once. But just to give you a hint of what's open still. For example, we don't know yet if pi plus E is transcendental, or really we don't even know if it's irrational. This is one of those cases where no one thinks pi plus E could possibly be rational, but no one has any technique to prove one way or the other. All right, and I should mention that, I mean, this is one of these numbers that my collaborators are fond of saying, that if you were to show, transcendental or even irrational, it is the kind of question which would give you an immediate Fields medal. They'll ship it to you immediately. And I must admit that our methods do not apply to pi plus E. E is not going to be the kind of integrals that we can deal with. But there are many other interesting numbers under the sky, and we'll be able to tackle them. By the way, can you hear me still? Is everything good?
Yeah.
Yeah, okay. Actually, I will try something here as I shift gears. How about now? Can you hear me?
Yes, we actually hear very well, at least me.
Yes, okay, good. Now I can hear you all the time, so if you want to interrupt, it's maybe even better. So the voice is good, huh?
Yeah.
Good. All right, now let me kind of set up the next 10 minutes of the talk. Here, there are some numbers that are going to be out of our reach. The problem of showing transcendence is still way, way open. Even this one single example is way open. So you have to choose your battles. You cannot attack showing transcendence for every number. And what I'm going to do is describe in the next minutes or so which numbers I will concentrate on. And I'll essentially take a page out of the book of from the 17th, 18th century mathematicians, and we'll study certain values of simple functions. Let's begin with a very simple kind of function. We'll say a function is algebraic. Let me add over q bar. And for my talk, Q bar is embedded into complex numbers. And it's the algebraic closure of rational numbers. So F is algebraic over Q bar if there is a polynomial call it maybe P of X, Y. And let's say this is a function of X, such that P of X, Fx is U. And I want a non-zero polynomial. So clearly it's a generalization of algebraic numbers. And let me give you some baby examples to get us warmed up. Say the square root of a polynomial or a cube root or nested square roots and cube roots of polynomial functions, they would all be algebraic. You want to be careful not to have constants here that would be transcendental. If you want to use a constant, that constant will be algebraic. Now, I mentioned I will use values of functions. So functions are kind of easier to study than numbers. And that's what you're doing here. We're picking a easy kind of function. For example, you might ask, well, I mean, there were these, I can't even decide whether a number is algebraic or transcendental in general. What about functions? Because you can study the growth rate of functions, it's actually fairly easy typically to decide whether it will satisfy a polynomial equation or not. You send x to infinity, you study the growth rate of f, see what it will do to a polynomial. And there are many more tricks to show whether a function is algebraic or not. So this is a safe space for us. And now I make the following simple observation. If I take an algebraic number and f algebraic over Q bar, then the value of f at alpha is also algebraic. I mean, you can see that I'll just plug x equals alpha here, keep the y as a variable, and you see f of alpha annihilates a polynomial with Q bar coefficients, hence it's algebraic. So the values of f didn't help me so much. I don't get anything new, but we're just a step away from this. The antiderivative of f will not have this substitution. And here, I'm making this comparison, especially to make the connection to the algebraic numbers. So I had functions whose values at Q bar were again would give me algebraic numbers. I'm essentially moving one step away from them. I'm going to take their antiderivatives, their integrals, and they will give me all kinds of numbers and many transcendental numbers. Right, so I'll give you many more examples later on, but for instance, if alpha is an algebraic number, let's say number 0, then I can consider the integral from 1 to alpha of, let's say, the algebraic function 1 over x. This is even a rational function, it's very simple. And this is going to be log of alpha. So depending on which path you choose from 1 to alpha, it will give you the appropriate branch of the logarithm. And log of alphas are in general transcendental. For example, you can get you can get 2 pi I as even a closed loop integral. 2i is algebraic, pi is transcendental, so this number is transcendental. Okay, so that's the kind of numbers we'll study, will then be definite integrals of algebraic functions where the endpoints are algebraic. So I'll now just set up the theory and the kind of the geometric perspective of studying those kinds of numbers. Good. So let's do this. The numbers that I've been describing are called one periods, and let's set this up correctly and set up the notation. So first, we can take an algebraic function, and the set of algebraic functions you can denote with this qx bar. But I'm going to integrate these things, so sometimes it's reasonable to attach a form dx here. That's the right object. So let fx dx be an algebraic form defined over q bar. So I will skip, let's say over q bar. And now I need to describe what kind of integrals I'm allowed to use. So, and gamma be a path for a one cycle on, for now, let's just cheat and say C minus the poles of my form. Let's call this omega. C minus the poles of omega, such that the boundary of gamma lies inside Q bar. So I don't care what the path does everywhere else, but its endpoints should be in Q bar. Then the integral called an elementary one period. So this is, I mean, I gave it an auxiliary name. Just you can view it as this integral is essentially the antiderivative of my algebraic function f, and I'm integrating it between the endpoints of gamma, which are algebraic. So it's essentially an evaluation of the antiderivative of f at algebraic points. And yeah, so this elementary one periods have that convenient representation. It's a finite representation in the sense that f can be represented using a polynomial with algebraic coefficients. So that's good. Gamma seems kind of flimsy. So this looks like it wouldn't have a finite presentation, but I can deform gamma if I fix the endpoints. This is just Stokes' theorem kind of argument here, that the value of the integral will not change. So I really am looking at just the homology class of gamma, and I can, for example, find a representative that's rectilinear. So it's just a bunch of straight lines with vertices at algebraic points. And that would make gamma also finitely represented. That's not what we would use. There are better ways of representing this, but it's just to represent the integral in principle can be represented by a finite amount of information. So you cannot do this with every real number. So I've given some very simple examples here. Upstairs, this was the logarithm. Let me give you maybe a slightly different example. Oh, first, let's expand this. So a one period is a Q bar linear sum, elementary one periods. And we'll be studying Q bar linear relations between these kinds of numbers. To give a slightly more interesting example than the logarithms, let's take a number, algebraic number that's not 0 or 1. Then I can consider the elliptic integrals So let's say Tx x times f minus 1 times x minus lambda, and over some path with nice endpoints. So these are called elliptic integrals. And this is one kind of slightly more complicated than the numbers I just demonstrated here. And it's one of the classical numbers that have been studied before. But now you will notice, and I've been hiding this under the rug thus far, this square root function is multi-valued over the complex plane. So it's really that I should not be using the complex plane. You can get away with it because our paths are simply connected. So you can define a value along the path canonically by just fixing one of the values over the path. And this is how people used to study these kinds of integrals in whatever 18th century. But after Riemann, people would use here the Riemann surface of f or omega. So really, this is an integral over a curve, so an algebraic curve. And let's just set that up too. That's how we're going to get ourselves into a proper theory. So let's C be the Riemann surface of f. So this will be the Riemann surface of the algebraic curve, where f is single valued. So the values of f are well defined here. So that if p, x, y, so annihilate f, we can use components the zero locus of p in, let's say, C2. Of course, I would then resolve singularities and compactify, but so we're right now just doing theory. These operations are free in theory. So that's C. But the point is, on C, I want to connect to something that's a little bit more rigid. These integrals are too flimsy right now for my test. What you can do is, I want to consider, let's say, something like the cohomology of C. We've already seen that I can deform gamma. I can also deform omega by exact forms if I do it correctly. So we must do it correctly. But the problem is, omega, the differential form that I want to study, might not be available on C. For example, the curve that would support 1 over x is P1, but P1 will not have 1 over x dx as a sort of a representative of a form of its cohomology class. So what you do, one way to handle this issue, is to define C0 be C minus the fold of the differential omega. And let's just give this a name, maybe D or something, for the boundary of gamma. Boundary of gamma, that's going to be, when you do this operation properly, the boundary is actually on, the path is on C, the boundary is on Q bar points of C. And what you might consider is the class of omega in the, what's called the algebraic de Rham cohomology of C0 relative to B. So this is similar to the de Rham cohomology in that I'm going to have differential forms, modulo exact forms, except the algebraic de Rham cohomology does not just do differential geometry. It's an algebraic construction, and this is a Q-bar vector space. So you become sensitive to these issues. When you try to check for transcendence, I cannot work with a real or complex vector space, so the usual de Rham cohomology, because scaling my numbers would destroy the transcendence properties. So it's important that I have access to a theory where the cohomologies are Q-bar vector spaces. And similarly, the path gamma, really, I just need the class of gamma and the KP cohomology of C0 relative to D. So this relative to D business here just says I'm allowed to have boundary. My paths are allowed to have boundary on D. Well, I kind of hooked up my D appropriately. For cohomology classes, it's a bit more delicate, but it's just sensitive to changing omega with respect to exact forms. When you change something via exact forms and you're integrating over something with boundary, the fundamental theorem calculus says the changing y-exact forms is not going to come for free. Your integral will change by the value of f at the boundary of gamma. And if f is algebraic, I'm sorry, I think I used f. Let's call this h. If h comes from the function field of C with Q bar coefficients, then this number would also be in Q bar. So in principle, it doesn't worry me. But the number does change, so we build the appropriate cohomology layers here. So this gets rid of the issue with the path. The beta cohomology is finitely generated, abelian group. We don't see torsion, so you can mod out by torsion, and it's a free. So it's a z to the m for some m. And one more thing here. So the pairing between omega and gamma. So before it was an integral, but you can view it purely cohomologically. So let me squeeze that over here. So the integral of omega over gamma, this is the cohomological pairing between gamma and omega, or rather using the duality between first cohomology and first homology. After you tensor those things by the complex numbers. And here's the interesting bit, that this transcendental number is entirely captured by the comparison between two cohomology theories, between de Rham cohomology and Betti cohomology. And this was the idea, to study isomorphism between different cohomology theories, to study numbers. And this is the general engine behind the theory of periods. Good. So let's I talked about relations between numbers. So let's make that a proper definition. So if you give me a bunch of complex numbers, at least I can define the space of Q-bar relations between them. And define Q-bar relations between these numbers to be the set of tuples of algebraic numbers such that bi alpha I sum is 0. And in particular, I want to emphasize this is the Q-bar vector space in k-dimensional Q-bar vector space. So this would always be finitely generated. You can, if you had the means of doing so, you could exhibit this relation space by giving me a basis. And there would at most be k elements in your basis. So I would like to make a small restriction now, a remark between the kind of numbers I want to study. So I want to distinguish between the value of one period, so value of an integral, and the representation of that integral by a way of exhibiting the form omega and some way of exhibiting gamma. And that I'll just call the integral representation. And there's no need to be fancy, and you can just say the tuple. You can give me a tuple, the curve and omega, and as discussed, you can make that a finite representation. So I have access to that number in terms of objects that I can, in principle, manipulate. And now here's the theorem. So I should say this is a theorem in progress, but we're almost there. And I'm certainly aiming for 2024. So what I want to say is that if you give me periods, I should be able to tell you algorithmically the cubar linear relations between them. You can give me the integral representation of some numbers, one periods. Finitely many one periods. By the way, one periods are sums of elementary one periods, but you can just represent that sum as giving me the integrals of each term and the coefficients, the algebraic coefficients that you're using. Anyway, it doesn't matter. You can also work with elementary one periods. It's the same result. And it will output a basis for the space of relations. And so I'll show you that this has some, well, very simple applications of this thing. So this theorem says quite a bit. Very simple applications you will recognize as quite interesting, I hope. For instance, so the number 1 is an integral of dx from 0 to 1. So 1 is a period. This is the 1 period. Therefore, if alpha is a 1 period, then compute the cubar relation between alpha and 1. And this vector space will be the 0 vector space if alpha is transcendental. And not 0 if alpha is algebraic. Well, since I compute a basis for this vector space, and well, a basis for 0 is the empty set. So if my algorithm would terminate and give you the empty set if alpha is transcendental. Otherwise, it will give you a relation. And by looking at the relation, you can also recognize which algebraic number is alpha. Let's do one more kind of simple application. Well, here's the kind of problem that you have in general. In this case, we can solve it now. Let alpha and beta be one period. So in general, if you give me two integrals, and you're giving me the integral representation, that's what I know. You give me two integrals like this. And in general, it's a very hard question to decide if the corresponding numbers are equal. This is a very important problem in general. So we've chosen these one periods because the way the integrals are a very frequent way in which nature presents us with numbers. So we want to deal with these kinds of natural representation of numbers, and yet we cannot even check equality in general. Yeah, so, but in this case, of course, you can run the algorithm. There's also another way, but here you can just compute the relations between alpha and beta and check if 1 minus 1 comma minus 1 is inside this Q-bar vector space. So if I give you a basis for this vector space, you can certainly make that check in finite time and therefore decide equality. I should mention that it's super open. And conservation idea in their exposition on periods status as one of the key problems. So given, I'll just call it n periods, so n-dimensional integrals of algebraic functions. Any variable algebraic functions. Can we check equality? So of course, they're asking for essentially an algorithm, but it's not even known right now, let alone giving me an algorithm. Right now, in general, it's not clear that there would exist an algorithm to decide equality for period integrals. So if you increase the dimension, you cannot go check equality. So dimension 1 is a special case where this theory is mature enough that we can do this. Any questions so far?
So you said, Emre, there is another way other than your algorithm, right, to decide the equality in one dimension?
Well, yes. So in principle, there's something here. When checking equality of 2-1 periods, there's a theory that's been developed by Caudron in late 90s, I think, where he studies, well, in let's say the arithmetic of algebraic commutative groups, and he describes, well, he would give you, if you give him alpha and beta in some sense, he should be able to give you a number, let's say epsilon, that should separate alpha and beta if they're not equal. So that means what you would do is that you would start approximating alpha minus beta. And if your approximation of alpha minus beta is so small that it's smaller than the epsilon that Caudron gives you, you can decide equality. The problem is, so he had, I mean, his theory was developed without any intention of ever making this explicit. So that he says, in principle, this computing this epsilon should probably be explicit, but they don't know how. And so the paper has like 50 bounds that are computed. Each bound is saying that there exists a bound that does this, there exists a bound that C, it goes up to C subscript 50. So each of them would have to be computed, or you'd have to figure out whether they're computable to be able to get his bound. So this theory is, I mean, his theory is very interesting. It was published in Finance, I think. So that's, we were able to decide equality in principle, but not in practice.
Emre,
Yeah.
Can you comment a bit on how to prepare the input for your algorithm?
Yeah, that's the integrand is kind of easy, right? So you would give me the minimum polynomial of the thing you're integrating.
Mm-hmm.
But wait, actually, what's next on my agenda? Well, the thing that's trickier is giving the path, maybe. But even that, so let's say your f, this is kind of a stupid example, but just to do it quickly. let's say f is square root of 1 minus x squared. All good. So f is 1 minus x squared. Then you know I can take pxy to be y squared minus 1 minus x squared. Or this is the equation of the circle. Yeah, so you could give me this p. In general, that's how I accept algebraic functions or algebraic forms.
Right.
And then, well, I will just construct the ZP. Well, essentially, it's closure in P2 if you want, I don't care. This is C bar, some singular curve. Yeah, it resolves singularity C. I would resolve the singularities only in my mind. I don't need to do this in practice. And now talking about giving the curve gamma, well, maybe you've seen this. I'm sure you have. So I have the x coordinate gives me a map to P1. So I have x everywhere. So the x coordinate gives me a map to P1. So I can compute the homology of C from essentially homology of P1 minus the branch points.
Mm-hmm.
And people do this by even constructing a Voronoi diagram around the branch points on P1. That's essentially C. So just I have finite many points on the complex plane C. You construct a Voronoi diagram around those points. And that would give, that's a graph now, the homology of that graph, which is very much computable, very discrete object, it projects onto the cohomology of C, and you can compute the kernel. That's easy. And if you want to put punctures or make relative homology, I mean, it's just clear. You just add more points to represent your punctures, or you allow your graph to have sort of endpoints. And so you work with the homology of a graph in the end.
Thanks.
Yeah, sure. By the way, the Gaudron's principle, we talk a lot about Gaudron's work here, checking equalities. So for instance, it cannot handle transcendence. And so you'd have to give it 2 1 periods, and it can, if they're equal, it can check if it's equal, but it cannot search for all possible relations. So I must mention this. So this application will be new. So instead of going into, well, the fancy theory, so if I have time, I will state at least the cornerstones of the theory that we're using. I want to digress a little bit and go to 1960s, where I think the spirit of what we're trying to do is truly captured by the work of Baker. You just have to reinterpret his work. And this is a digression on linear forms in logarithms, algebraic numbers. So what I'm going to do is I will start with K algebraic numbers. So these are not the periods I'm going to use. I will work with their logarithms in just a second. But I take non-zero algebraic numbers and consider the abelian group I'll just write Z to denote this is an abelian group generated multiplicatively in Q bar star. So Q bar star is a group under multiplication. I give you a bunch of numbers. You can just generate a subgroup generated by those numbers. And with finitely generated abelian group, it has a rank, for example, and I'll use this rank. So the theorem of Baker from 1967. So he got a Fields Medal for this result. And it was a generalization of Gelfand-Schneider from the 30s. It was, what was the year exactly? 1934. And which solves Hilbert's seventh problem. Gelfand-Schneider would handle 2 algebraic numbers. And that's also the context of Hilbert's seventh problem in interpreted correctly. So here's Baker's theorem, sort of reinterpreted with modern context, if you want. You consider the rank of this algebraic, this very much algebraically described, finitely described object, the rank here, you add 2, you'll see why. And then this is going to give me the dimension of Q-bar linear relations between 1 and 2 pi I. So that accounts for 2. These are independent of everything else. And then the logarithms of So I take the logarithms of my algebraic numbers. So what's very impressive here, so this is a Q-bar vector space. I compute the dimension. Inadvertently, I'm getting something about the relations. In fact, I'll make these relations precise now. But you see the left-hand side, you don't need to know anything about how you would compute it, but you can sense immediately that it's very much computable, the left-hand side. It's very much algebraic. The right-hand side is a priori transcendental. And so Baker's contribution is to say that you can translate this completely transcendental problem into an algebraic problem. And let me actually explain to you why you might have, you could hope for such an equality, and whether actually knowing this equality allows you to get all linear relations, Q-bar linear relations between these numbers, the logarithms of alpha i's, 1 and 2 pi I. One more thing, I didn't tell you what is the logarithm of alpha. So there are many different branches, but it doesn't impact the dimension because I have 2 pi I here. Different branches of logarithm will just differ by multiples of 2 pi I, so I don't care. Now here's a simple example. Let's say alpha 1 is maybe 4 roots of 2, and alpha 2 is, say, the 4th root of 2 times I. Now here, you can probably spot immediately that the rank will drop here. The multiplicative group generated by alpha 1 and alpha 2 will have one multiplicative relation. Oh, sorry, the 4th root, maybe I don't think. So we have, if I take the 4th power of alpha 1 and the reciprocal of the 4th power of alpha 2, so this will give me alpha 1 divided by alpha 2, the 4th power. This will give me 1. So that's the multiplicative relation, implying that the rank here will not be 2, but instead 1. And of course, I can take logarithms down to get that 4 times the logarithm of alpha 1 minus 4 times the logarithm of alpha 2 is 0 modulo choice of branches. So I'll say modulo 2 pi I. We don't care about this. Which means that every multiplicative relation gives me a Q relation, Z relation, between the logarithms. But conversely, if you give me a Q relation between the logarithms, I can just clear the denominators, get a Z relation between the logarithms, and just collect the log terms. And then I get a multiplicative relation between the alpha i's. So there's a relation between what's on the left-hand side and the Q dimension of the Q vector space generated by these numbers. So what Baker is able to say that there are no new Q-bar relations between those numbers. Every relation comes from Q relations, which are multiplicative. So let me add Baker's contribution here in this form. So the left-hand side is equal to the dimension of the Q dimension of the Q vector space generated by these numbers, which we agreed is purely algebraic. So the equality from left to the red is trivial. His contribution is to show that the Q-bar relations and the Q relations agree. And maybe to put this in context, oh, by the way, because of the technical issues, I started apparently 10 minutes late. That's okay. I want to go the full 60 minutes, but you can tell me to stop and I'll just wind down somehow. So to tie it back to one period, let me just say how Baker fits into the story. So I mentioned that there were curves underlying our integrals. The integrand immediately gives me an algebraic curve. And the genius of this algebraic curve gives you essentially a filtration on the kind of numbers that you can construct. And Baker's theorem is about the first filtration, about the genus zero curves that appear. And this would be that if you take a one period, so where f is not just algebraic, but it's a rational function. So the polynomial annihilating it would have a degree 1 in the f variable or the y variable. Then, so actually you can say, or the genus of the Riemann surface of f is 0. Then the integral is a linear sum, bar linear sum of 1, 2 pi I, and logarithms algebraic numbers. And it's very easy to see this. You just have to do partial fractions on f. You do partial fractions. There will be certain things that you can. Antiderivative is again a rational function, and there will be only terms left with pole order 1, and their derivative are logarithms. So it's an easy lemma, but it just puts this thing in context. Okay, so here's what I want to do. I want to state essentially the new theoretical development that allows us to algebraize essentially the relations between one periods, and then I hope that gives you a sense of how we think about this problem. Okay, so first thing first, let's introduce the algebraic, the objects I'm going to use. These are called one motives. Unlike the general theory of motives, it's fairly accessible. So first of all, I need to define an algebraic torus. P over Q bar, something which is something isomorphic to the multiplicative group and k copies of the multiplicative group for some k. So in particular, the complex points of C, you might recognize as C star to some power. And for example, Baker was studying one copy of C star. If you increase copies, it doesn't matter this is all you have. But this, we have kind of Baker-like situation here. And what we need to increase the genus is to introduce a semi-abelian variety. Zero goes to T injects into G, there's a choric kernel, and there's an abelian variety A. And finally, so this is a torus, this is a semi-abelian variety, and a marking on G is a lattice, let's say, lattice here used to mean just some Z M with a map to Q bar points of G. Yeah, so what Baker was doing was his G had trivial part A. He had one copy of C star, and he was marking alpha 1 through alpha k. Those would have been the algebraic points of GM. And then you have lattice Zm if you're marking m points going into the GQ bar. So that information has a name, the lean pointers term. So marked semi-abelian variety. Okay, you denote it as such. It's one mod. Morphisms are morphisms of complexes. So it's a complex with two terms, essentially. And we invert multiplication by an integer, so up to igogeny. So that's so important right now. And he says, well, this category is abelian. The category of one mod is abelian. And here's his real contribution, and this is why he called these things one motifs. And so the RAM and Betti functors from relative varieties. So varieties pairs. X, Y, where Y is an X. And so I had such a thing. I had the curve and a bunch of points in the curve. So we can do this generally. And you can compute their first cohomology. He says the first cohomology of any variety or relative variety factors through one motifs. And in particular, the one motifs has also functors which are called H1 and H1 Betti and H1 Deram that go from one motifs to various vector spaces, Q bar vector space and Q vector space, the same. And let me translate this for you to like a human translation. So every one period, in fact, more generally construed, even you can go to higher dimensions if you use one forms and integration over paths. Every one period has an algebraic representation, namely the one motif, in an abelian category. And the holy grail for doing such motivic constructions is to say it's not just the numbers that have an algebraic relation, but in fact, the categorical relations now in the category of one motifs. So it's a abelian category, meaning the category behaves like the category of modules or almost like vector spaces. So then there are decompositions in that category. And the dream was to have that the relation between numbers of one periods and categorical relations coincide. So this has been established a couple of years ago. And Huber and this was so they say that not only are the numbers algebraizable in the sense, so it has an algebraic interpretation, but they say the relations, I should say maybe Q bar relations between periods, one periods, arise from short exact sequences in the category of one motifs. Of one motifs. So that means if I have a short exact sequence like this, and here the motifs are essentially abelian varieties. That's a special case of this. So you can think of pulling back a differential from form from M double prime and pushing forward the loop from M prime. And then the integral is certainly 0 because it's just a projection formula. The integral here on M would mean the integral of the differential form of M double prime over the image of the loop from M prime to M double prime. But that image is just a point. So let's give those things a name and let me just write down what I'm saying. So the integral of pullback of a form from M double prime integrated against the push forward of a cycle. This would be the same as pushing forward gamma all the way to M double prime, but that's just, this is the point, kind of the 0 point, M double prime, if you see it as a group of omega, and that's a one form integrated over a point, which is 0. So if you have short exact sequences, it's a triviality, just like Baker's theorem, that one direction is a triviality. If you have short exact sequences, you have many relations. So this is in the cohomology, you would not know something is a pullback, push forward, whatever. In cohomology, there would be some 0, and it could be realized because something is a pullback and something is a push forward. And they say that actually every relation can be accounted for by short exact sequences in the category of one motives. And well, our contribution is to make that effective. We will, given the Jacobians of punctured curves and markings on them, we simplified this problem a little bit to make it a problem that can be computed in finite time. So we don't search through all motives. We search over decompositions of only one motive. And here the problem is, this is not a semi-simple category. Short exact sequences do not split. So finding short exact sequences is another problem. And the set of short exact sequences is not simple. So there are certain reductions to be made. And well, that's our contribution to figure out how to make this effective. All right, I'm out of time, so I'll stop here. Thank you very much.
Thank you, Emre.
Thank you very much. It's an excellent talk, Emre.
Thank you very much.